Okay, we're on section 5.4, applying quantum mechanics to electrons in atoms, and I'm going to skip the warm-up and go to starting with hydrogen, one-on-one. And in a previous section, we were talking about a guitar string to explain standing waves for the allowed energy states for electrons that were in atoms. And if we solved Schrodinger's wave equation for the allowed energy states for hydrogen, we would see that each energy state had its own numbers and its own types of orbitals. And the equation shows us that the higher the energy, the greater the number and types of orbitals that are present. And when you're looking at an atom, there are three-dimensional electron waves or orbitals that are more complicated than a guitar string. And so to describe them, I have to use something called quantum numbers. Each quantum number is going to describe something different about the orbital and the electrons that we're looking at. We're starting with the principal quantum number n. And the principal quantum number n indicates the relative size of the atomic orbital. And if you take a look at the periodic table, the one that has all of your nomenclature notes on it, that one might be easier. If we label it n equals 1 through 7, okay, that is your principal quantum number n that we've just labeled. And those are the allowed energy states for the electrons, and those are all positive integers. And if we take a look at the text, and we go on to the next page, where we have the second quantum number, which is a script L. This is known as the angular momentum quantum number. And this is related to the shape of an atomic orbital. And the different values for L correspond to whether we are looking at an S, P, D, or F shape. So what I mean by that is if you have an L value of 0, that means you're looking at the S, or spherically shaped sublevels that exist in an energy level. If you're looking at an L equals 1, then we are looking at a P sublevel or orbital shape, which is a dumbbell shape. If you're looking at an L value of 2, we are looking at a D. And for the Ds, these are cloverleaf shapes. And then if you're looking at an L value of 3, you are looking at an F sublevel or orbital shape. But that has no specific shape associated with it, so I'm not going to give it any further description here. Now, the question is, when I'm looking at the periodic table back here, how do I know where my L equals 0, 1, 2, and 3? Well, it's really, really simple. If you look at the very first 2 columns on your periodic table, and I'm going to put a little X through this hydrogen over here, and I include helium in that. This is where my S's are. That means this is an L value of 0, as is this box here that has helium in it, okay? Then if I go on to an L value of 1, I'm looking here. These are the P's, kind of interrupted by the 3, 4, 4, 3 trick that you've got going on down here. But the L equals 1 value starts here at boron, goes over to neon, and is this box right here. Then if you're looking at the D's are everything in the middle. So this is where my L value is 2. So it starts over here where scandium is, and it goes over here to zinc, and includes everything here that's in the middle, okay, this rectangular portion. Then where my L equals 3, that's going to be down here, this entire rectangular box that's detached. These are all of the F's, and that's where my L is 3. Okay, so now one thing that I need to explain to you is that each energy level has one new orbital shape in addition to those existing in a previous level, And this is typed up here in your book. It's like the first paragraph underneath this highlighted portion, the very first sentence. Each new energy level has one new orbital shape in addition to those existing in the previous level. What does that mean? If I'm looking at n equals 1, I have the s's. Remember, these are all s's here. So all I have present is an s. If I go to n equals 2, I have s's here, where lithium and beryllium are, but when I cross over, now I have p's. In n equals 3, I have an s here, so this would be considered 3s, and then when I cross over, this is 3p. So just to reiterate, this is the beginning of 1s right here. I have hydrogen and helium and s's. And then if we think of each box for each element as I have an electron in each box, okay? When I come to the second energy level, this is the beginning of 2s. I have 2 electrons in 2s here, where lithium and beryllium are. Then I cross over, this is the beginning of 2p. I have 1, 2, 3, 4, 5, 6 boxes in 2p. So I can hold 6 electrons in 2p. Then I come over here to 3, n equals 3. This is the beginning of 3s. I have 2 boxes here. I can hold 2 electrons in 3s. And then I cross over. This is the beginning of 3p. I have 1, 2, 3, 4, 5, 6 boxes in 3p. I can hold a maximum of 6 electrons. Then you're probably wondering, well, how can I have one more sublevel or one more orbital shape? Well, technically, the D's lag behind the period that they're in, or the energy level that they're in. If this is n equals 4, where scandium is, this is technically the beginning of 3D. So I have 3s, 3p, and 3d. The D's have 10 boxes. That means they can hold a maximum of 10 electrons. Once I get into n equals 4, this is the beginning of 4s, where potassium is. I have 2 boxes that can hold 2 electrons. I'm skipping over the D's because that's 3d. This is the beginning of 4p, where gallium is. I have 6 boxes going over to krypton. I can hold a maximum of 6 electrons in 4p. And then down here, where yttrium is, that's the beginning of 4d. Now, I should have one more orbital or one more sublevel or one more shape, which I do because technically the F's lag 2 behind the period that they're in. You will notice lanthanum here, number 57, from 57 down here to 58. Okay, this is the beginning of the F. So technically this entire row fits up right here in between LA and HF. And since the F's lag 2 behind and this is the 6th period, this would be the beginning of 4F. So we have 4S, 4P, 4D, and 4F in the n equals 4 energy level. I think you get the idea. So n equals 1 has 1S or an S. N equals 2 has an S and a P. N equals 3 has an S, a P, and a D. N equals 4 has an S, a P, a D, and an F. Now, if we go on to the third quantum number, which is m sub L. The third quantum number is known as the magnetic quantum number, and this is telling us the 3-dimensional arrangement or the orientation in space for a given atomic orbital. Now, this can be a little bit confusing to students, so let me explain. M sub L is equal to plus or minus the L value for your location. You probably can't see that because there's a light glare there. You can probably see that. It has to do with its location on the periodic table. So let me pull the periodic table back up and let me try to explain this in a little bit more depth. So what I'm going to do with this periodic table is, let's make it bigger. That's kind of too big. Let's bring it down a little bit. Okay, so what I'm trying to show you here is I have my n's, okay? I have my L equals 0 here. We cross this hydrogen out. I have my L equals 1 here, whereas this is L equals 0. I have my L equals 2 here. And then way down here, I have my L equals 3. I'm just going to write L equals 3 for everything down here that's detached. Now, I'm going to try and label this so that you can see it fairly well. If my M sub L value is based upon my L value, that means that my M sub L value here is plus or minus 0. So that means my M sub L is just 0 for these two, for my S's, which would also be here. Your M sub L value would be 0 because M sub L is plus or minus your L value, okay? This will make more sense as I go along. If my L value is 1 here, my M sub L value is plus or minus 1. I start with negative always. Then I go to 0. Then I cycle back up to plus 1. Then I go all the way back to negative 1, 0, plus 1. These are the possible M sub L values for the P's, okay? Now, for an electron that is in the D's, your possible M sub L values will be plus or minus 2. We start with a negative 2 here above scandium. I'm going to put a negative 1 here, a 0, plus 1, plus 2. I cycle back, negative 2, negative 1, 0, plus 1, plus 2. Now, you might think what I'm telling you is that if you have an electron here, then it could only have an M sub L value of plus 1. That's not what I'm saying. All of the possible M sub L values for an electron in the P's are negative 1, 0, or plus 1. All of the possible values for M sub L for any electron in the D's would be a negative 2, negative 1, 0, plus 1, or plus 2. It just happens to fit this way on the periodic table. It's like somebody planned it, okay? If I'm looking at my L value of 3 down here, my M sub L values would have to start at negative 3, because this is 3. I would go to negative 2, negative 1, 0, plus 1, plus 2, plus 3. Negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. Okay, so the magnetic quantum number M sub L is showing you the orientation of space of an atomic orbital. These are the number of possible different orientations in space, which also represents the number of individual orbitals of that particular shape or sublevel. Okay? Only a single s orbital exists at any given energy level because s's are spherical clouds. So if I'm looking at, here's my x, y, and z axis, if I'm looking at a spherical cloud created by electrons that are outside the nucleus, they can only exist three-dimensionally in one place, which would be within that sphere, okay? But if I'm looking at something else like a P, if you turn the page, the P's have got, I don't know how much room I have here, I'll attempt to draw it. You have an X, a Y, and a z-axis to convey 3 dimensions in space. And if you think about it as electrons, if I can have a maximum of 6 electrons in a P, then they want to get as far away from each other as possible. So I'm going to have one electron first going on the x-axis. Then the next one is going to go on the y-axis to get away from the other one. And then if I have a third electron, it's going to go on the z-axis to get away. Then they will start pairing up. Then the fourth electron would go on the x-axis, the fifth electron would go on the y, and the sixth electron would go on the z. And when they orient themselves this way, the P's get these dumbbell-like clouds about the x, the y, and the z-axis, okay? That's why we have -1, 0, and +1 repeating, because this is describing, so to speak, where the electrons are going and on which axis, Okay, so it's saying you'll first have an electron at one axis. We'll have that be the -1 value describing its three-dimensional place in space, and then 0 for another axis, and then +1, and then it would go back and pair up with -1, 0, and +1. Okay? Now, if I'm looking at the next page here, here are your orbitals, your p orbitals, which I just drew on the board, okay? And they're showing you 2px. This is just describing the electrons that are on the x-axis, okay? And here are the ones on the y, here are the ones on the z, and here they are all together. And if you're looking at the value n squared, this tells us the number of orbitals existing in the nth energy level. So for example, if I'm looking at n equals 2, and I take 2 squared, I get 4. That tells me I have 4 orbitals in the n equals 2 level. I have 1 2s, and I have 3 2p orbitals. Now I may have just confused you, so let me go back for a minute and let's take a look at that periodic table that I had. Each s holds a maximum of 2 electrons. 1, 2 can go in 1s. 1, 2 can go in 2s. 1, 2 can go in 3s, and so on. So that means I have a single orbital that holds 2 electrons max. If I'm looking at the p's, they can hold 6 electrons max, but I can't have 6 electrons altogether. I can only have 2 maximum. So since I have 6 electrons, the p's will have 3 orbitals total. And these orbitals are typically drawn in orbital diagrams. What I mean by that is, and I'll get to this a little bit later, if I'm looking at 2s, you'll simply see maybe a box or a line representing an orbital, and then you'll have electrons in that orbital drawn as half arrows, sometimes as whole arrows, and they point in opposite directions. Here for the p's, I have 1, 2, 3 orbitals. I can put a maximum of 6 electrons total in all 3, but you can only put 2 electrons in each orbital, okay? So that's where this concept of how do I figure out how many orbitals I have. If I'm looking at the D's here in the middle, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. I can hold 10 electrons. That means I need 5 orbitals, 2 each. For the F's down here, I have 14 boxes. That means I can have 7 orbitals total, holding all 14 electrons, okay? Okay, now, for the D's, the clover leaves, you are not going to be asked to draw this. This is just here showing you how those clover leaf shapes would appear. And if we come down here, you would see that each higher energy level introduces another sublevel with a greater number by 2 of more complicated orbitals than the previous ones. So there are 7f, 4f orbitals with more complicated shape than the D's. So what this means is as I progress from S's to P's to D's to F's, the S's hold a max of 2 electrons. So they have 1 orbital that can hold those 2 electrons. And then the P's can hold a maximum of 6 electrons, so they will have 3 orbitals. The D's can hold a maximum of 10 electrons, so they will have 5 orbitals. the F's hold a maximum of 14 electrons, so they will have 7 orbitals. So here I am showing you that I am increasing by 2 more complicated orbitals every time, okay? Okay, now in terms of energy, if you take a look at the next page, you'll see that they've given you an energy diagram with the orbitals present for hydrogen, and you'll notice that 1s is the lowest energy, and then 2s followed by 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. And each one of those circles is representing an orbital, okay? I wouldn't necessarily memorize that. It's just kind of there as a reference. If you follow the periodic table, you'll see the energy increasing as you go row by row. Let's take a look here at the quick check. State what each of the 3 quantum numbers described above tells us about atomic orbitals. Well, n is the principal quantum number, and this is the size of an atomic orbital. Then we have L, which is the angular momentum quantum number, and this tells us the shape. Then we have M sub L, and this is the magnetic quantum number, and this tells us the orientation in space of that particular quantum number. Number 2, what is the difference between a 1s and a 2s orbital? Okay, if it's an S is a spherical cloud, okay, around the nucleus. So they have the same shape, but in terms of shape, is one bigger than the other? Yes. This 2 here tells you that this is a larger orbital than the 1s, and the electrons are going to spend time further away from the nucleus in the 2s than they would in the 1s. So what I mean by that is, if I'm looking here, this is my x, y, and z axis. If I'm looking at a 1s, it might look like this. So the electrons would be there, close to the nucleus. But if I'm looking at the 2s orbital, this is going to be a much larger sphere. So that means that the electrons are going to be further away from the nucleus, and this will be larger. B, what is the difference between a 2px orbital and a 2py orbital? So they both have the same shape, right? A p is a dumbbell shape. And they have the same energy levels, right? They are both 2, so they have the same quantum number. But the x and the y tell you that the orientation in space is different. This would be on the x-axis. Okay, so this is your 2px. And then I would have some also on the 2py. Number 3, how many different orbitals are available to an excited hydrogen electron in the 4th energy level? Okay, so m squared is going to tell you how many orbitals you have. Since we're in the 4th energy level, n equals 4, that means this is 4 squared, so there are 16 orbitals total available. If I look at the periodic table, you'll see you would have, in the 4th energy level, a 4s, a 4p, a 4d, and a 4f. So remember, there is 1 orbital in each s. There are 3 orbitals in p's, 5 in d's, and 7 in f's. So if you add all of these together, you get the 16 orbitals. last quantum number. All right, this is the spin quantum number. The spin quantum number is abbreviated as M sub s. It tells us that there are two possible electron spins, a positive 1/2 or a minus 1/2. The positive 1/2 is usually called spin up. The negative 1/2 is usually called spin down. What does this mean? If I have an orbital, let's say I have a 1s orbital with 2 electrons, electrons orient themselves in opposing directions because they have the same charge. So you would refer to the one here that's pointing up as a positive 1/2, it's spinning up, and the one pointing down is a negative 1/2 or a spin down. Technically, we never really know whether it's positive 1/2 or minus 1/2. We just kind of say that there are two possible values for the spin quantum number. So a single electron can actually create a little magnetic field of spinning charge. And so electrons seem to spin in one direction while the remainder spin in another. And that's where this whole concept comes from.